Greetings, mathophiles. Welcome to a video in which we will not address important theorems or thorny issues of concept. We're simply going to get mechanical and take a look at three different ways of re-expressing an integrand so that we can complete the integration by hand. You'll see our subject on the screen. It's the indefinite integral 2x plus 6 all over x minus 1 dx. The first approach we're going to take is that of division of the numerator by the denominator. This can be a very useful technique in situations where you have a rational function and the numerator is of greater or equal degree to the denominator. And we catch a bit of a break here because our divisor is linear, so we can divide synthetically. We don't have to divide the long way, so to speak. So we have 2x plus 6. Our divisor is x minus 1. Pull down the 2. 1 times 2 is 2 plus 6 is 8. And so our quotient is 2 with a remainder of 8 over x minus 1. And so our integral becomes integral 2 plus 8 over x minus 1 dx. And now life is easy. Nothing easier than integrating a constant. This remainder term, except for the 8 and the subtracted 1, is just a log, but there's no chain rule there. There's nothing multiplied by the x or anything like that. So this is just going to be 2x plus 8 natural log absolute x minus 1 plus a constant of integration. Once we achieve the re-expression, this is an easy integral. Our second approach will be to make a substitution. This is a fairly standard integration technique that sort of comes out of the chain rule. If you're unfamiliar with it, this channel may have a future video on it. Otherwise, there are many other sources that you could consult to learn how that works. We're just going to assume that you have some knowledge or familiarity with it, and we're going to go ahead and use it. So we're going to re-express this by writing it in terms of u, where u is equal to x minus 1. And our reason for this is that we would like to have a monomial term in the denominator, because then that allows us to split the integrand into multiple terms. Odds are they're going to be simpler and more tractable than the thing that we're presented with initially. So du is dx, and x is u plus 1. So if I re-express this in terms of u, I have integral 2x, which is u plus 1, plus 6 all over u du, when we've achieved the intended effect of having a monomial in the denominator. If I take a line to distribute the 2 and collect like terms, this is integral 2u plus 8 all over u du, and this starts to bear some familiarity to what we just saw. If I split this now into two terms, which has become legal with the single term below, I have 2u over u, which is 2, plus 8 over u du. That is pretty easy to integrate. That is 2u plus 8 ln absolute u plus constant. Now it's appropriate to recall that u was x minus 1. So this is 2 quantity x minus 1 plus 8 ln absolute x minus 1 plus our constant of integration. If we distribute the 2, we see something that at first blush might be a little bit concerning, but in fact is not a problem. And that is that we have an extra 2 here as compared to the result that we got using the first method. But 2, after all, is a constant. And if our result and the result from the previous method only differ by a constant, then we're fine. In fact, I could even rewrite this and just say, okay, now I have a new constant, C1 or something, which is the old C minus 2. And then they have a look that should concern no one. So that is our second method, substitution. Our third method is called partial fraction decomposition, or simply partial fractions. If you're an AP student, it may be of interest to you that this is a BC rather than an AB integration topic. But some of you may have even learned how to do this in an Algebra 2 or a pre-algebra class in a context that would be disconnected from calculus. Anyway, it goes like this. We imagine that our integrand, the 2x plus 6 over x minus 1, is the sum of two other fractions, and that the denominators of those fractions are factors of our denominator. And you might say, well, we only have the x minus 1, but we're going to imagine that 1 is also a factor of x minus 1, which technically it is. And so we're going to suppose that our integrand is the sum of fractions with those two denominators. If we knew the numerators, we would have a re-expression that might be of help to us as we try to evaluate the integral. The reasoning for this is somewhat beyond the scope of this video, but there are plenty of good sources on it, and this channel may have a video on partial fractions in the future. Anyway, we're going to take this and multiply through by the x minus 1. So we have 2x plus 6 equal to a times x minus 1. So that's ax minus a plus b. Now for these two expressions to be equal, the coefficients on the x terms have got to be equal, which means a has got to be equal to 2. And the constant terms have got to be equal, which means op a plus b has got to be equal to 6. Which means, since a is 2, b had better be 8. And so now we are in a position to integrate 2 over 1 plus 8 over x minus 1 dx. And that, mathophiles, is an expression we've already seen. This was the form that we ended up with in the first example when we divided the numerator by the denominator. So I won't continue beyond this point. You can scrub back to the first part of the video if you want to recall how that worked. Those of you who are experienced integrators will know that most of the battle is picking out the right method in a given situation. So I hope it's been helpful to see these three different approaches to this one rational integrand. In a given situation, probably the best one is the one that occurs to you first. Although if you have more than one idea about how to approach an integral, I think most of us would choose the one that we anticipated would be the least aggravation, the least work. Sometimes you're right about that, and sometimes you're not. Integration is a process where you just have to feel your way around. It's not like differentiation where it's very straightforward and you just have to combine the right rules in the right order. So I hope this will be useful to you going forward in your attempts to integrate by hand. Happy mathing.